Okay, we were discussing about paging in the last class, and then we were saying that every process can be given its own page table. Every process can be given its own page table, and so this is how it works. So I have process P1, I have process P2. Each will be given a 4 GB virtual space, assuming a 32-bit architecture. Okay, and essentially here both of these processes will need operating system routines. I explained you last time. So some part of this will go for the operating system. Why it needs operating system? Why every routine will need every process will need operating system? For basically performing the system calls, etc. Right? So and even your page translation mechanism, everything is part of your operating system. Okay, so some part of the virtual address space will be given for this, and the remaining entire space is available for the process. Well, this is OS. Now, what actually happens is within this part of whatever this part, there will be the page directory also mapped. Okay. Now, in the physical page, this is the RAM. Again, some part will be used for the OS. It will be reserved for the OS. Okay. So when I load, when P1 is executing, its page directory. So let me just zoom that page directory here. Its page directory will have some parts which will map onto the OS. Okay, and then there will be lot more of parts here, but then what happens is that when P1 is executing, let there be some K frames, all the frames will not be given to P1. Okay, so in the physical memory, please note carefully, in this physical memory, say some part will be allocated to P1. Say let us say some 5 frames will be allocated to P1, 5 page frames. Then some part will be allocated to P2, say again some 7 frames. Even though P1 is given the entire 4 GB of address space, it has to, when P1 is executing, the OS pages are mapped here, and there are only some pages. All the pages here have to get mapped onto these 5 pages. So for me to execute this entire program marked in green here, I have only 5 pages that are given for me. So I have to use, say this can be say 2 power, let us say 2 power 20 pages. So some are used, so let me say 2 power 20 minus epsilon pages. That many pages are actually available to the compiler, so the program can be as large as this. But then what happens, all these programs by demand paging has to get executed only using these 5 page frames. So at most 5 pages from this will be in the memory, and then they will be swapped out. Similarly, so what happens is the page directory of this will map this OS page onto this RAM, and the remaining pages whatever here will be basically mapped on, whatever I am using here will be mapped on to these 5 page frames. So there will be at 5 valid entries for these pages. The remaining whatever pages are there for this process is using, those pages will be just invalid. and as and when I keep moving from pages from here to here and moving it back and forth, the corresponding entries in this page table will be changed, right. So as far as the compiler is seeing, it sees this entire address space, but as far as actual execution, it will have only 5 pages plus the OS page. So the entry for the page table corresponding to P1 will have entries for this OS, plus will have entries only for this 5 frames, right. And so the physical address will be restricted to these 5 frames, and where that physical address will stay will depend upon which of those 5 pages are loaded, right. There can be 5 pages here loaded, the corresponding entries will point to these 5 frames, maximum 5 frames. When this process P2 starts executing, then again the OS page will be loaded, and then there can be at most 7 pages from this lot. Say, let us say 100 pages, there will be only 7 pages actually loaded into this maximum, right. And the remaining 93 pages will be invalid. Which of those 7 pages are loaded, that depends upon your execution. Are you able to follow? And there will be no more entry in this page table other than these 7 page frames. So if at all this process has to execute, that whichever page is necessary has to be loaded into one of these 7 frames and executed. I can't go and look at some other page frame other than these 7 page frames. When this process P1 is executing, it can only execute on using these 5 page frames on the RAM. It cannot go and use anything more. By this, I am getting you an isolation between these 2 processes, right. So when I am loading the page table itself, only these pages are valid, these page frames are valid. So I can't go and use any other page frame other than these, and this is what is your physical memory. So I actually get a complete isolation between P1 and P2. Are you able to appreciate this? So how is protection, inter-process protection ensured by paging? This is how it is ensured, okay, right. Now the biggest drawback between the segmentation and this is that this is only protection between the processes, but in the same process itself, intra-process protection sort of things cannot be ensured here, right, because now I don't have a way of specifying that this is a code segment. I don't have a way of specifying that this is a stack segment. I don't have a way of saying this is a data segment. I say it's a page, okay, right. But I can certainly say that P1's frames and P2's frames I have isolated. So when P2 starts executing, it will load some of these frames from the memory to the from the hard disk to the main memory. Now when P2 finishes, or let us say there is a round robin scheduling, P1 executes for some time, then P2 and vice versa. When P2 is executing, it will bring some frames into this, it will bring some pages into these frames. When it shifts to P1, then what will happen? P1 will also bring some frames here. Again when I shift back to P2, I will reuse those frames here. Are you getting this point? So every time, so that means when P1 is executing, actually P2's instructions are still in the RAM, but P1 will not be allowed to touch those things because of my paging mechanism. And again when P2 is executing, P1's frames that it has brought, it is still in the RAM, but P2 will not be allowed to touch it because of this paging mechanism. And virtually P1 and P2 will be given 4 GB address space. Are you able to follow this? That is why when you do the task switching in your next assignment, you will find that CR3, the context of a process will also have this CR3 register. That means I could have a page directory for each process, and since a page directory is only 4 KB, and then I will have at most 1 or 2 page tables. So with 3 pages I can maintain the complete virtual memory per process. So this per process paging is what is very, very important. Are you able to get this? Okay. Now going forward, how did I decide? So what is the immediate question that will come in your mind? How will I decide that P1 needs 5 frames, P2 needs 7 frames? How will you guess this? Seriously, there is no answer for this question, okay? Because if I say I have a very large program, right, it does not mean that it is going to take a large execution time, right. If I have a very short program, it does not mean it will quickly finish off. Can you give me one example of a very shortest program that you have seen which will take enormous amount of time?
Infinitely.
Huh? Infinite, but let us say complete a program that will eventually complete.
Very long loop.
While one is something that is, but that nobody will, let us talk of a sensible program, but it will take, shortest program but it will take lot amount of time. I think CS 100 we have taught you.
Some huge time factors.
Right? Fibonacci will finish off in linear time. The shortest program that will take largest amount of, probably great grandchild will finish, see the end, that type of thing. But say 7 to 8 line program.
Prime factorization.
Prime
factorization.
factorization is a big prime factorization that you have written in your life. Towers of Ni, right? Have you done towers of Ni? Right? It will take 2 power n time. N disk, moving n disk from one tower to another tower, such that a small disk should not be on top of the larger radius disk should not be on top of the smaller radius disk. So I will have some n disks in one thing. Sorry, and then I have to move these 4 disks to this. I can use one more rod here, but the large. Hey, don't say that you don't know towers of Ni. Do you know or not? Yes, right. So this takes 2 power n time. So they have started, by the end time you finish this Kali Yuga will finish or something, some stories also like that. So that's, so you cannot say just by looking at the size of the program, you cannot say what is the memory that I need to allocate for it, right. I could have a very large program, but it will be just one straight line code. I could have a very small program that will be spanning across. Say suppose P1 has 90% of P1 will execute on 6 pages. Then if I have just 5 frames, then I am gone. I need at least 6 pages there. So then my thing will work. Please note that a page fault is a very costly affair. Why it is a very costly affair? Because I land up with a dirty page, worst case. I have to find out which page to replace. I have to copy that page back and then copy this back. So a page fault will kill performance. So we need to see that if I allocate the frames, then my page fault should reduce. You all understand what a page fault is, right? So the objective here is to reduce the page fault. So I have to allocate that many frames so that the page fault actually gets reduced, right. So there are 2 ways of looking at it. Operating system course will teach you this. When they do memory management in operating system course, they will teach you this in great detail. There are 2 types of allocation. One is called static page allocation, or page frame allocation should be called static frame. Another is obviously dynamic page frame allocation. What is static page frame allocation? When the program is about to become a process, when the program starts to execute, at that point of time I say these are all the pages, these many pages, page frames are allocated to you. I will give it 3 page frames at the time of start. I will give 3 page frames at the time of start. Then what will happen? That 3 page frames will be there for entirety. I do not dynamically change the number of page frames, right. But there is another thing called dynamic page frame allocation, where I see the program behavior and I keep allocating more pages. As the program is executing, I make a decision of how many page frames I need to give to it, right. So if the number of page frames allocated to a process is determined before execution of that process, then it is called static page frame allocation. When the number of page frames necessary is decided while I am executing the process, then I can put machine intelligence there, see what is happening. I could intelligently keep increasing the number of page frames, decreasing it, etc. Right? Then it is actually called dynamic page frame allocation. Okay. So what are different static page frame allocation techniques? What are different dynamic page frame allocation techniques? This will be taught in great detail in your 5th semester operating system memory management part of your course. But as far as this is concerned, yes, I allocate some frames and I use those frames, and that is very important from an architecture perspective, because I can't say that the entire RAM will be erased and reloaded when I switch from one process to another, because I do lot of work as process P1 or actually as process P2. I spend lot of time to bring 7 frames here. The moment there is a context switch, these 7 frames in the RAM cannot go off. It has to be there so that I get performance. Otherwise, every time when I do a context switch, I go and fetch the entire thing from virtual memory to RAM. It's impossible. Then your performance will be even much slower than a Turing machine. Okay, right? So you have to be extremely careful in doing this. Are you able to follow what I am trying to convey here? So page frame. So as a process comes in, to sum up, a process comes in, it has its own page table. Every process has its own page table, and the virtual memory of that process is basically filled up with some amount for OS. What are the things inside that OS? You are already seeing, you are seeing some GDT, LDTs, now this page table. Then you will see something more like process block, etc. We will see as we go on to the next assignment for task switching. So these are the things that will be there on the OS part. So every fellow has to have this OS, right? And then the entire remaining space is dedicated in the virtual address is dedicated to the process. But then on the physical side, this entire process will be allocated some constant number of page frames, which it will use to shift in and shift out pages to complete the execution. So this is the entire setup. And the objective for the page replacement and page allocation, so there are how many pages should I give you, and what is the replacement strategy I need to follow. These two things are taken care of by the operating system. Okay. So the next interesting thing is the question, how do I, the objective of this entire exercise is that I need to go and reduce the number of page faults. If there are more number of page faults, then my performance is going to decrease tremendously. Now let us look at this. Okay. Now the way I can reduce page fault is to give more page frames. Correct? It's an obvious way of doing this. Now let us say that there is a program which is, what are the maximum value? 3210? Okay, 4. So it is using say 5 pages. That is a program which is using 5 pages. So let us say 0, 1, 2, 3, 4. Okay, 5 pages is it. And I am giving it only 3 pages in the memory. The number of page frames I am giving is only 3. Okay. And the replacement strategy that I am following is the first come first served thread. Which came first will go off, removed, right? So the first in first out rather than first come first served, it's called first in first out. Okay. Now let us say I am giving only 3 pages. So initially, so these 3 pages, initially everything is empty. So the first page, so what is that number? 3210? 3210? 321004. Okay. So this is the way the pages are accessed. First the program will start accessing page number 3. It starts, main is there, some routines are compiled above, so it starts. So nothing is here, so 3 is a page fault. So 3 gets loaded. Now this is the start. Okay. Next 2 comes, 2 is a page fault. Next 1 comes, 1 is also a page fault. Now 0 comes, who gets replaced? 3 gets replaced. So this is, now 3 comes. Now who gets replaced? So these, all these have been page faults. Now again 2 comes, who gets replaced? 1 gets replaced, right? Now 4 comes, who gets replaced? 0 gets replaced. Right? Now 3 and 2 does not have any page faults. 3 is there, 2 is there, it's already there. Again 1 comes, now 1 comes, this fellow gets replaced. Now 0 comes, then 4 comes, there is no, 4 is already there in the middle. So how many page faults it cost? 9 page faults it has cost, right? Right? So the program, what if this is called, this is the page sequence, page access sequence. The program started executing from page 3. It executed a lot of instruction page 3, then it started accessing page 2. It is not that this instruction is page 3, next instruction is page 2. What you see by this sequence is page 3 fetch, I will execute a lot of things there, then go to page 2 at some point, and then. So this is the page access sequence. It is not, it does not mean that instruction 1 is in page 3, instruction 2 is in page 2. You got it? I bring page 3, execute something, then bring page 2, and then so on. So totally 9 faults were there, 9 page faults happened, in which please note that the first 3, 2, 1, etc., they were all compulsory faults. They are called compulsory faults, because they had to be loaded. The remaining thing got were basically because we loaded something and now we undo it and then load something. So after 3, 2, 1 came, 0 got reloaded, right. So this is called compulsory faults, page faults, and the remaining called conflict page faults. They came because of some conflicts. 0 came in because 0 was not there in that page, but it was not that there was an empty, so everything was filled, and so we went and replaced something and put 0. We replaced something with 0. So that is why we call it as conflict page faults. Okay. So totally 9 page faults happened. So I am not very happy with this 9. I need to go and reduce this. So what is the next way of reducing it? Give it 4. Now what happens? 3 is a page fault, 3, 2, 1, 0 are page faults. Then next 3 and 2, and the next 3 and 2 are all page hits because 3 and 2 are here. The next is 4. So what will happen to 4? 4 will get loaded here, sorry. 4 will get loaded here. The next was 3. So 3 will get loaded here. the next was 2, the next was 1, the next was 0, the next was 4. So, the number of page fault now is 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. By increasing the number of page frames, the number of page faults actually increased, it did not decrease, correct, right. So, earlier case it was just 9, now it is 10, right. This anomaly you and me could have found out, but well before our birth Beledy found it. So, this is called Beledies Anomaly. Okay. So, by the end of your thing you also find out some anomaly, say, okay. So, you can put your name there. Okay. Now, this is called Beledies Anomaly. What do you mean by Beledies Anomaly? What is the consequence of Beledies Anomaly? Just by increasing the number of page frames, I cannot go and decrease the number of page faults, right. So, the way a program executes is not capturable by some method. Now how can I rectify Beledi's anomaly? So there is a theorem which is very straightforward to prove. If a page replacement, I will call it as PR, if a page replacement algorithm follows the stack property, then it is devoid of Beledi's anomaly. If a PR algorithm follows the stack property, right, then it is devoid of Beledi's anomaly. What is the stack property? The set of pages loaded in RAM for k page frames is subset of RAM pages loaded for k plus 1 page frames. So, I use this algorithm for given k page frames. At every instance there will be some set of pages loaded. Now, I increase the number of page frames to k plus 1 and again run the algorithm, again run the program. At every instance there will be some set of pages loaded, right. Now, the set of pages loaded for k page frames should be a subset of the set of pages loaded for the k plus 1 frames. Then Beledi's anomaly will not happen. Okay. Why Beledi's anomaly will not happen? If Beledi's anomaly happens, how do you argue this proof? Let us come to the proof later, but let me show here. So, what has happened? Initially 3 alone was there, then 3 2 was there, then 3 2 1, then 0 2 1, 0 3 1, then 0 3 2, then 4 3 2, 4 3 2, 4 3 2, then 412, then 410, okay, and then this is again 410. Now let us do this 3, 3, 2, 3, 2, 1, 3, 2, 1, 0. So this is 3, 2, 1, 0, 3, 2, 1, 0, 4, 2, 1, 0, 4, 3, 1, 4, 2, 1, 4, 3, 1, 0, 4, 3, 2, 0, 4, 3, 2, 1, 0, 3, 2, 1, 0, 4, 2, 1. Okay. Now you see 3 and 3 there is no issue, 3, 2 there is no issue, 3, 2, 1 there is no issue, 3, 2, 1, 0 there is no issue, 3, 2 there is no issue, 3, 2 there is. But when I take this 4, 3, 2, right, this is 4, 2, 1, 0, but that is 4, 3, 2. So this is not a subset of this, right. And let us take this 4, 3, 2, this is 4, 3, 1, 0. So this is not a subset of this is not a subset of this, that corresponding location. Again here 4, 3, 2, right. So these are the reasons why this whole thing goes into a big problem. Are you able to follow? Right. So essentially what has happened, the stack property is violated by the FCFS. FCFS does not ensure that the set of pages loaded in RAM for k page frames is a subset of set of pages loaded for k plus 1 page frames, and that is precisely the reason why we land up with this Beledies anomaly. Are you able to follow? Now, can we go and prove Beledies anomaly? Can you go and prove this statement, that if a page replacement algorithm follows the stack property, that means set of pages loaded in RAM for k page frames is subset of RAM pages loaded for k plus 1 page frames. If this satisfies, then it is devoid of Beledies anomaly. Can we prove this? What is the way we can prove? What is the shortest way of proving this?
Page fault in k plus 1 will also be page fault in k.
No, that was not, no. But page fault is okay, but I want to say that it will not increase. If the stack property is satisfied, then if I increase my page count in page frames allocated to a process, then the number of page fault will eventually has to decrease. But in this case it increased. How can you go about this proof? So give me a proof, very quick proof.
Contradiction.
Proof by contradiction. Somebody said, now what will you contradict and what will you prove? Proof by contradiction is correct.
Suppose it increases. Then
What you
number of
contradict?
page faults increases, suppose.
So I have algorithm A satisfies stack property, but still, right, number of page faults given k page frames, still number of page faults given k page frames is greater than number of page faults given
K minus 1.
k minus 1 page frames. Correct? That means, so this is the contradiction. Algorithm A satisfies stack property, but still number of page faults given k page frames is greater than number of page faults given k minus 1 page frames. That means this implies there exists at least one instance wherein a page P belongs to k page frames, page P does not belong to k page frames, but P belongs to k minus 1 page frames, right. This implies, right, because there should be some instance where k minus 1 does not suffer from a page fault and k suffers from the page fault. The instance of k page frames suffers, then only I can get this more, right. So this implies this violation of stack property. Hence, if my algorithm satisfies stack property, then as I keep increasing the number of page frames, my page fault will decrease. Unfortunately, in the case of FCFS, since stack property is violated, Beledies anomaly can basically creep into it. Are you able to follow? Okay, right. So what we will do is, in the afternoon class, I will talk about a little more about paging, and these are all now, this and the next chapter will be more towards operating system, because as you see we are slowly moving towards operating system concepts. Okay. So we will discuss more in the afternoon class. Okay. Thanks.